This is Module 8, Lecture Note 16. At the top of your notes today, I want to do just a really quick review of what we learned in last lecture, which was ionic bonding. Okay, so this top section, I'm going to label ionic bonds. Remember, a metal is going to give its electrons to a nonmetal. An element on the left side of the periodic table is willing to give up some of its electrons to a nonmetal so that they both can fulfill the octet rule. And remember, that means they both want 8 valence electrons in their outer shell. When the metal gives its electrons to the nonmetal, it has a charge. It gets rid of a negative friend and becomes positive. The nonmetal gains an electron or a negative friend and becomes negative. This attraction between a positive and a negative ion is what holds the bond together, and that is an ionic bond. Okay, a bond formed by the attraction between positive and negative ions. Think of it like a magnet. Opposites attract, and so they're going to be held together by that attraction. Okay, so just remember that whenever you draw ionic bonds, you should always show the giving of electrons, and you should also show charges. Okay, and so there's just 2 reminders for you. Charges and giving of electrons anytime you are doing ionic bonding. Okay, so let's jump down to the next section and we're going to look at covalent compounds. Remember, covalent compounds contain only nonmetals. Okay, so they are going to be bonds that are formed between these elements here on the right side of the periodic table. For example, if we want to bond F2, okay, we want to bond a fluorine to a fluorine. Okay, remember, you can find the number of valence electrons by looking at the column. Fluorine is in column 7, so it's going to come in with 7 valence electrons, and this one will have the same. Okay, so in this case, they are both 1 away from having a full octet, and neither one of them wants to give up an electron. So the only way to make both of them happy is to have them share an electron pair. So the way that you can show that is by showing that these 2 electrons will be shared between them. Okay, so sometimes this fluorine has possession, sometimes this fluorine has possession, but when they're bonded together, both of their octets are full, and this is a covalent bond, and they will remain together like that. Sometimes you will also see it shown like this. The covalent bond is represented by a straight line. Those are shared. And then the other electrons are on the outside. Okay, and I like the way this looks. It looks nice and neat to me. And that's the shared pair. Okay, so you can be kind of flexible with where you put the shared pair. I like it between them. Remember, these electrons are rotating around the atom, so they're not actually fixed on these exact sides. This is just a representation of that, and this would be the shared bond between them. This is a covalent bond, a shared pair of valence electrons that holds the atom together, and it can be represented by a line or 2 electrons with a circle around them. Okay, so in this example, it's really easy to see which electron pair needs to be shared in order to bond the 2 fluorines together. But when we get into some larger molecular or covalent compounds, we're going to follow this general set of rules for how to bond these covalent compounds together. It says you're going to add up the total number of electrons, and you might just note that this is the valence electrons. And you're going to divide by 2. That's going to tell you how many lines to draw in your picture. So let's do that first step together for CCl4. I like to do a little bit of math off to the side. I have 1 carbon, and it comes with 4 valence electrons. I have chlorine, which gets 7, but notice I have 4 chlorines. So that's going to give me 28 valence electrons. I'm going to add the total number of valence for my whole compound, which would be 32. And I'm going to divide that in half, and it's going to tell me how many lines I need to draw in my picture. Okay? This will make sense when you see my first drawing. I'm going to put my carbon in the center. And the general rule is that if you only have one of something, it should be in the middle of your picture, and your other elements should branch outward from it. So I'm going to connect my chlorines on all 4 sides. Okay? I know that I need to connect my chlorines with a line. That's the only way they will stay covalently bonded to that carbon. So I've already used 4 of my lines that I'm allowed to draw out of the 16. I've used 4, and then you're going to go around and you're going to fill up the outsides of your outer elements to complete your number of valence electrons. So I would say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And that would complete my bonding picture. This represents everybody having a full octet. Carbon has 4 lines touching it, or 8 electrons. Chlorine has 4 lines touching it, or 8 electrons. Remember, a line is the same thing as 2 electrons. So this would satisfy my total valence, and it would satisfy the octet rule for everyone. I would like you to jump to SIBR4. It should look very similar, and you should be able to do this one the same way following what we just did. All right, here's what you should have for SIBR4. It also has 16 lines, so you bond the bromines to the silicon and make sure that everybody has a full octet. Let's jump over here to another 2 examples that'll look a little bit different when we work them out. Hydrogen is in the first column, so it comes with 1 valence electron. And oxygen has 6. Okay, I have 2 hydrogens, so I need to make sure I get both of those, and then I'm going to add together. 2 plus 6 gives me 8 valence. Divide that in half. I'm allowed to draw 4 lines in this bonding picture, or 4 pairs. Following our rule that we talked about, you're going to put the element you only have 1 of in the center. And then you will bond your other elements to it. And you can bond them on any side. I'm just going to bond them here. Okay. I've used 2 of my lines. Now, where do I put the remaining 2? Okay, it is super important that you see this exception here. Put the other atoms around the center atom. Make sure each atom has 8 electrons or 4 lines touching it. But hydrogen is only allowed to have a total of 2 electrons or 1 line touching it. Okay, remember we said that hydrogen, it wants to be like its nearest noble gas. And that's helium. Helium is such a small atom, it only has 2 electrons. So when hydrogen tries to fulfill its octet, 2 is its maximum number, and that is an exception for hydrogen. So my other lines need to go on oxygen, so that oxygen has 4 lines or 8 electrons to complete it. Okay, I've done the math for this last one. I have 3 carbons and 8 hydrogens, giving me a total of 10 lines. Go ahead and check your math on that. So what am I going to put in the center since I have 3 carbons and 8 hydrogens? Whenever you get something like this, this is called a hydrocarbon. And you need to form a carbon chain. Okay? The carbon is going to form a backbone of your compound. And what I mean by that is you're going to link these carbons together like a backbone. Then your hydrogens can branch off of your carbons. So I've already used 2 lines. I need to connect 8 hydrogens, and I think there's enough sides to do that. 2, 3, 4, 5, 6, 7, 8. You want to double check how many lines you've used in your picture, and I think we've actually already used our 10 lines that were allowed. Let's make sure we're not breaking any rules. Hydrogen is only allowed to have 1 line. Carbon is supposed to have a full octet, so each carbon, if you were to single it out individually, should have 4 lines around it. And they do. So this is a completed bonding picture for C3H8. Okay, on the back, we're going to look at some more complicated Lewis structures. They're going to follow the same rules. However, we're going to be creating some double or triple bonds. On the first page of your notes, these single lines are called single bonds. Okay, a single line represents a single bond. On the back here, we will be creating double or triple bonds in some cases in order to fulfill the octet rule. So you're going to start every problem the same by adding up your valence electrons, dividing by 2, and figuring out how many bonds or lines that you're allowed in your picture. In this first example, we are bonding oxygen to another oxygen. Okay, and if you want to use a pencil for these, you can. We know that we need to at least connect them by 1 bond so that they stay together. Now, I still have 5 other lines I'm allowed to draw in my picture. 1, 2, 3, 4, 5. I'm going to just place them on the outside of the atom, and then I may need to do some shuffling in order to fulfill the octet rule. Let's look at just this oxygen. Is it happy with 8 electrons or 4 lines? It is. But this one is not. It only has 3 lines. So what you may have to do is move a line inward so that it can be shared between them. And this creates a double bond. Now, if you look at each oxygen individually, they both have a full octet. So it may be handy to use a pencil until you figure out exactly where your bonds should be in case you have to move them. This is a double bond. Okay, let's jump down to N2. Nitrogen comes with 5 electrons, and we have 2 of them. So that's going to give me a total of 10. And I'm allowed to make 5 lines. Okay, I'll have my 2 nitrogens. Remember, they have to at least be connected in the middle by 1 line. And then I can go 3, 4, 5. I kind of just always put them spread out on the outsides, and then I reevaluate. This one only has 3 lines touching it, and that one only has 2. So in this example, we're going to need to bring, oh, I get to draw another line. 1, 2, 3, 4, 5. Okay, we still need to do some rearranging here. We're going to need to bring 2 sets of electrons into the middle so that they can be shared between them. Now this nitrogen has 1, 2, 3, 4, 1, 2, 3, 4. This would be a case when you need a triple bond. 3 sets of electrons that are shared. Okay? So my general rule of thumb that you can write here is that you're always going to give the electrons to the outside atoms first and then move them inward if you need to. Always place lines on outer atoms first, then move inward to fulfill the octet rule. Okay, I'd like you to do the math for these last two problems, and then we'll look at the drawings together. This is CO2, carbon dioxide. We have one carbon, so it should go in the center of your picture, and the oxygens should be connected to your center atom. I'm allowed 8 lines, so I've used 1, 2, put the extras on the outside atoms, 3, 4, 5, 6, 7, 8. I've got all my 8 lines on paper. Now I may need to move them around to fulfill the octet rule. The oxygens are happy with 4 lines each. But we can see that the carbon needs some more bonds to it. And the only way to satisfy that is to move one pair on each side inward. So you can erase or you can cross them out, and you can move a bonding pair inward so that now carbon has 4 lines and each oxygen does as well. So you will have double bonds to your carbon, and then you will have extra pairs on each oxygen. That's what carbon dioxide should look like. And then lastly, we have CH2O, and I figured out 6 lines or 6 pairs. I'll want to put the carbon in the center. Remember, carbon is a good central atom when you have just one of them, and you can connect your hydrogens and your oxygen to the carbon. Now I've used 3 of my lines and I'm allowed 3 more. Am I allowed to put any more on these hydrogens? No. Hydrogen is only allowed to have 1 line touching it. So I have to put my extra electrons on the oxygen. 1, 2, 3, 4, 5, 6. Do I need to move any inward? Carbon only has 3 bonds to it, so you will need to erase or cross out one of your pairs on oxygen and create a double bond. This is how your final answer should look for CH2O. Hydrogen is happy with 1 bond to it, carbon should have 4, and oxygen should have 4. These will take some practice. The more of them that you do, you'll start to get a picture in your head for how it should look. But here's some general rules of thumb that you can go by when you are starting to do these in your homework or in class.